global warming is the long-term rise in the average temperature of the Earth's climate system. It is a major aspect of current climate change, and has been demonstrated by direct temperature measurements and by measurements of various effects of the warming. The term commonly refers to the mainly human-caused increase in global surface temperatures and its projected continuation. In this context, the terms global warming and climate change are often used interchangeably, but climate change includes both global warming and its effects, such as changes in precipitation and impacts that differ by region. There were prehistoric periods of global warming, but observed changes since the mid-20th century have been much greater than those seen in previous records covering decades to thousands of years. The Intergovernmental Panel on Climate Change, IPCC, Fifth Assessment Report concluded, it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. The largest human influence has been the emission of greenhouse gases such as carbon dioxide, methane, and nitrous oxide. Climate model projections summarized in the report indicated that during the 21st century the global surface temperature is likely to rise a further 0.3 to 1.7 degrees Celsius, 0.5 to 3.1 degrees Fahrenheit, in a moderate scenario, or as much as 2.6 to 4.8 degrees Celsius, 4.7 to 8.6 degrees Fahrenheit, in an extreme scenario, depending on the rate of future greenhouse gas emissions and on climate feedback effects. These findings have been recognized by the national science academies of the major industrialized nations and are not disputed by any scientific body of national or international standing. The effects of global warming include rising sea levels, regional changes in precipitation, more frequent extreme weather events such as heat waves, and expansion of deserts. Surface temperature increases are greatest in the Arctic, which has contributed to the retreat of glaciers, permafrost, and sea ice. Overall, higher temperatures bring more rain and snowfall, but for some regions droughts and wildfires increase instead. Climate change threatens to diminish crop yields, harming food security, and rising sea levels may flood coastal infrastructure and force the abandonment of many coastal cities. Environmental impacts include the extinction or relocation of many species as their ecosystems change, most immediately the environments of coral reefs, mountains, and the Arctic. Due to the persistence of CO2 in the atmosphere and the inertia of the climate system, climatic changes and their effects will continue for millennia even if carbon emissions are stopped. Possible societal responses to global warming include mitigation by emissions reduction, adaptation to its effects, and maybe climate engineering. Countries work together on climate change under the umbrella of the United Nations Framework Convention on Climate Change, UNFC, which has near universal membership. The ultimate goal of the convention is to prevent dangerous anthropogenic interference with the climate system. Although the parties to the UNFC have agreed that deep cuts in emissions are required and that global warming should be limited to well below 2 degrees Celsius, 3.6 degrees Fahrenheit, in the Paris Agreement, the Earth's average surface temperature has already increased by about half this threshold and current pledges by countries to cut emissions are inadequate to limit future warming. Some scientists question the feasibility, in higher emissions scenarios, of climate adaptation. Observed temperature changes. Climate proxy records show that natural variations offset the early effects of the Industrial Revolution. So there was little net warming between the 18th century and the mid-19th century, when thermometer records began to provide global coverage. The IPCC has adopted the baseline reference period 1850 to 1900 as an approximation of pre-industrial global mean surface temperature. Multiple independently produced instrumental datasets confirm that the 2009 to 2018 decade was 0.93 plus minus 0.07 degrees Celsius warmer than the pre-industrial baseline, 1850 to 1900. Currently, surface temperatures are rising by about 0.2 degrees Celsius per decade. Since 1950, the number of cold days and nights have decreased, and the number of warm days and nights have increased. Historical patterns of warming and cooling, like the medieval climate anomaly and the Little Ice Age, were not as synchronous as current warming, but may have reached temperatures as high as those of the late 20th century in a limited set of regions. Although the most common measure of global warming is the increase in the near-surface atmospheric temperature, over 90% of the additional energy stored in the climate system over the last 50 years has warmed ocean water. The remainder of the additional energy has melted ice and warmed the continents and the atmosphere. The warming evident in the instrumental temperature record is consistent with a wide range of observations, documented by many independent scientific groups. For example, in most continental regions the frequency and intensity of heavy precipitation has increased. Further examples include sea level rise, widespread melting of snow and land ice, increased heat content of the oceans, increased humidity, and the earlier timing of spring events, such as the flowering of plants. Regional trends. Global warming refers to global averages, with the amount of warming varying by region. Since the pre-industrial period, global average land temperatures have increased almost twice as fast as global average temperatures. This is due to the larger heat capacity of oceans and because oceans lose more heat by evaporation. Patterns of warming are independent of the locations of greenhouse gas emissions because the gases persist long enough to diffuse across the planet. However, localized black carbon deposits on snow and ice do contribute to Arctic warming. The Northern Hemisphere and North Pole have warmed much faster than the South Pole and Southern Hemisphere. The Northern Hemisphere not only has much more land, but the arrangement of land masses around the Arctic Ocean has resulted in the maximum surface area flipping from reflective snow and ice cover to ocean and land surfaces that absorb more sunlight and thus more heat. Arctic temperatures have increased and are predicted to continue to increase during this century at over twice the rate of the rest of the world. As the temperature difference between the Arctic and the equator decreases, ocean currents that are driven by that temperature difference, like the Gulf Stream, are weakening. Short-term slowdowns and surges. Because the climate system has large thermal inertia, it can take centuries for the climate to fully adjust. While record-breaking years attract considerable public interest, individual years are less significant than the overall trend. Global surface temperature is subject to short-term fluctuations that overlay long-term trends, and can temporarily mask or magnify them. An example of such an episode is the slower rate of surface temperature increase from 1998 to 2012, which was dubbed the global warming hiatus. Throughout this period, ocean heat storage continued to progress steadily upwards, and in subsequent years surface temperatures have spiked upwards. The slower pace of warming can be attributed to a combination of natural fluctuations, reduced solar activity, and increased volcanic activity. Physical drivers of recent climate change. By itself, the climate system experiences various cycles which can last for years, such as the El Niño Southern Oscillation, 2 decades or centuries. Other changes are caused by external forcings. These forcings are external to the climate system, but not always external to the Earth. Examples of external forcings include changes in the composition of the atmosphere, for example increased concentrations of greenhouse gases, solar luminosity, volcanic eruptions, and variations in the Earth's orbit around the Sun. Attributing detected temperature changes and extreme events to human-caused increases in greenhouse gases requires scientists to rule out known internal climate variability and national external forcings. Therefore, a key approach is to use physically or statistically based computer modeling of the climate system to determine unique fingerprints for all potential causes. By comparing these fingerprints with observed patterns and evolution of climate change, and the observed evolution of the forcings, the causes of the observed changes can be determined. Scientists have determined that the major factors causing the current climate change are greenhouse gases, land use changes, and aerosols and soot. Greenhouse gases. Greenhouse gases trap heat radiating from the Earth to space. This heat, in the form of infrared radiation, gets absorbed and emitted by these gases in the atmosphere, thus warming the lower atmosphere and the surface. Before the Industrial Revolution, naturally occurring amounts of greenhouse gases caused the air near the surface to be warmer by about 33 degrees Celsius, 59 degrees Fahrenheit, than it would be in their absence. Without the Earth's atmosphere, the Earth's average temperature would be well below the freezing temperature of water. While water vapor, 50%, and clouds, 25%, are the biggest contributors to the greenhouse effect, they increase as a function of temperature and are therefore considered feedbacks. Increased concentrations of gases such as CO2, 20%, ozone and N2O are external forcing. On the other hand, human activity since the Industrial Revolution has increased the amount of greenhouse gases in the atmosphere, leading to increased radiative forcing from CO2, methane, tropospheric ozone, CFCs, and nitrous oxide. As of 2011, the concentrations of CO2 and methane had increased by about 40% and 150%, respectively, since pre-industrial times. In 2013, CO2 readings taken at the world's primary benchmark site in Mauna Loa surpassing 400 parts per million for the first time. These levels are much higher than at any time during the last 800,000 years, the period for which reliable data have been collected from ice cores. Less direct geological evidence indicates that CO2 values have not been this high for millions of years. Global anthropogenic greenhouse gas emissions in 2010 were equivalent to 49 billion tons of carbon dioxide, using the most recent global warming potentials over 100 years from the AR5 report. Of these emissions, 65% was carbon dioxide from fossil fuel burning and industry, 11% was carbon dioxide from land use change, which is primarily due to deforestation, 16% was from methane, 6.2% was from nitrous oxide, and 2.0% was from fluorinated gases. Using life cycle assessment to estimate emissions relating to final consumption, the dominant sources of 2010 emissions were food, 26 to 30% of emissions, washing, heating, and lighting, 26%, personal transport and freight, 20%, and building construction, 15%. Land use change. Changing the type of vegetation in a region impacts the local temperature by changing how much sunlight gets reflected back into space, called albedo, and how much heat is lost by evaporation. For instance, the change from a dark forest to grassland makes the surface lighter, causing it to reflect more sunlight. Humans changed the land surface mainly to create more agricultural land. Since the pre-industrial era, albedo has increased due to land use change, which has a cooling effect on the planet. Other processes linked to land use change, however, have had the opposite effect, so that the net effect remains unclear. Aerosols and soot. Solid and liquid particles known as aerosols, from volcanoes, plankton, and human-made pollutants, reflect incoming sunlight, cooling the climate. From 1961 to 1990, a gradual reduction in the amount of sunlight reaching the Earth's surface was observed, a phenomenon popularly known as global dimming, typically attributed to aerosols from biofuel and fossil fuel burning. Aerosol removal by precipitation gives tropospheric aerosols an atmospheric lifetime of only about a week, while stratospheric aerosols can remain in the atmosphere for a few years. Globally, aerosols have been declining since 1990, removing some of the masking of global warming that they had been providing. In addition to their direct effect by scattering and absorbing solar radiation, aerosols have indirect effects on the Earth's radiation budget. Sulfate aerosols act as cloud condensation nuclei and thus lead to clouds that have more and smaller cloud droplets. These clouds reflect solar radiation more efficiently than clouds with fewer and larger droplets. This effect also causes droplets to be of more uniform size, which reduces the growth of raindrops and makes clouds more reflective to incoming sunlight. Indirect effects of aerosols are the largest uncertainty in radiative forcing. While aerosols typically limit global warming by reflecting sunlight, black carbon and soot that falls on snow or ice can contribute to global warming. Not only does this increase the absorption of sunlight, it also increases melting and sea level rise. Limiting new black carbon deposits in the Arctic could reduce global warming by 0.2 degrees Celsius by 2050. When soot is suspended in the atmosphere, it directly absorbs solar radiation, heating the atmosphere and cooling the surface. In areas with high soot production, such as rural India, as much as 50% of surface warming due to greenhouse gases may be masked by atmospheric brown clouds. The influences of atmospheric particles, including black carbon, are most pronounced in the tropics and northern mid-latitudes, with the effects of greenhouse gases dominant in the other parts of the world. Minor forcings, the sun and short-lived greenhouse gases. As the sun is the Earth's primary energy source, changes in incoming sunlight directly affect the climate system. Solar irradiance has been measured directly by satellites, and indirect measurements are available beginning in the early 1600s. There has been no upward trend in the amount of the sun's energy reaching the Earth, so it cannot be responsible for the current warming. Physical climate models are also unable to reproduce the rapid warming observed in recent decades when taking into account only variations in solar output and volcanic activity. Another line of evidence for the warming not being due to the sun is how temperature changes differ at different levels in the Earth's atmosphere. According to basic physical principles, the greenhouse effect produces warming of the lower atmosphere, the troposphere, but cooling of the upper atmosphere, the stratosphere. If solar variations were responsible for the observed warming, warming of both the troposphere and the stratosphere would be expected, but that has not been the case. Ozone in the lowest layer of the atmosphere, the troposphere, is itself a greenhouse gas. Furthermore, it is highly reactive and interacts with other greenhouse gases and aerosols. Climate change feedback. The response of the climate system to an initial forcing is increased by positive feedbacks and reduced by negative feedbacks. The main negative feedback to global temperature change is radiative cooling to space as infrared radiation, which increases strongly with increasing temperature. The main positive feedbacks are the water vapor feedback, the ice albedo feedback, and probably the net effect of clouds. Uncertainty over feedbacks is the major reason why different climate models project different magnitudes of warming for a given amount of emissions. As air gets warmer, it can hold more moisture. After an initial warming due to emissions of greenhouse gases, the atmosphere will hold more water. As water is a potent greenhouse gas, this further heats the climate, the water vapor feedback. The reduction of snow cover and sea ice in the Arctic reduces the albedo of the Earth's surface. More of the sun's energy is now absorbed in these regions, contributing to Arctic amplification, which has caused Arctic temperatures to increase at more than twice the rate of the rest of the world. Arctic amplification also causes methane to be released as permafrost melts, which is expected to surpass land use changes as the second strongest anthropogenic source of greenhouse gases by the end of the century. Cloud cover may change in the future. If cloud cover increases, more sunlight will be reflected back into space, cooling the planet. Simultaneously, the clouds enhance the greenhouse effect, warming the planet. The opposite is true if cloud cover decreases. It depends on the cloud type and location, which process is more important. Overall, the net feedback over the industrial era has probably been positive. An analysis of satellite data between 1983 and 2009 reveals that cloud tops are reaching higher into the atmosphere and that cloudy storm tracks are shifting toward Earth's poles, suggesting clouds will be a positive feedback in the future. Roughly half of each year's CO2 emissions have been absorbed by plants on land and in oceans. Carbon dioxide and an extended growing season have stimulated plant growth, making the land carbon cycle a negative feedback. Climate change also increases droughts and heat waves that inhibit plant growth, which makes it uncertain whether this negative feedback will persist in the future. Soils contain large quantities of carbon and may release some when they heat up. As more CO2 and heat are absorbed by the ocean, it is acidifying and ocean circulation can change, changing the rate at which the ocean can absorb atmospheric carbon. A concern is that positive feedbacks will lead to a tipping point, where global temperatures transition to a hothouse climate state even if greenhouse gas emissions are reduced or eliminated. A 2018 study tried to identify such a planetary threshold for self-reinforcing feedbacks and found that even a 2 degrees Celsius, 3.6 degrees Fahrenheit, increase in temperature over pre-industrial levels may be enough to trigger such a hothouse Earth scenario. Climate models. A climate model is a representation of the physical, chemical, and biological processes that affect the climate system. Computer models are run on supercomputers to reproduce and predict the circulation of the oceans, the annual cycle of the seasons, and the flows of carbon between the land surface and the atmosphere. There are more than 24 scientific institutions that develop climate models. Models not only project different future temperature with different emissions of greenhouse gases, but also do not fully agree on the strength of different feedbacks on climate sensitivity and the amount of inertia of the system. A subset of climate models adds societal factors to a simple physical climate model. These models simulate how population, economic growth, and energy use affect, and interact with, the physical climate. With this information, scientists can produce scenarios of how greenhouse gas emissions may vary in the future. Scientists can then run these scenarios through physical climate models to generate climate change projections. Climate models include different external forcings for their models. For different greenhouse gas inputs for RCPs, representative concentration pathways, are used: a stringent mitigation scenario, RCP 2.6, two intermediate scenarios, RCP 4.5 and RCP 6.0. and one scenario with very high GHG, greenhouse gas, emissions, RCP 8.5. Models also include changes in the Earth's orbit, historical changes in the Sun's activity, and volcanic forcing. RCPs only look at concentrations of greenhouse gases, factoring out uncertainty as to whether the carbon cycle will continue to remove about half of the carbon dioxide from the atmosphere each year. The physical realism of models is tested by examining their ability to simulate contemporary or past climates. Past models have underestimated the rate of Arctic shrinkage and underestimated the rate of precipitation increase. Sea level rise since 1990 was underestimated in older models, but now agrees well with observations. The 2017 United States published National Climate Assessment notes that climate models may still be underestimating or missing relevant feedback processes. Effects. Physical environment. The environmental effects of global warming are broad and far-reaching. They include effects on the oceans, ice, and weather and may occur gradually or rapidly. Between 1993 and 2017, the global mean sea level rose on average by 3.1 plus minus 0.3 millimeters per year, with an acceleration detected as well. Over the 21st century, the IPCC projects that in a high emissions scenario the sea level could rise by 61 to 110 centimeters. The rate of ice loss from glaciers and ice sheets in the Antarctic is a key area of uncertainty since this source could account for 90% of the potential sea level rise. Increased ocean warmth is undermining and threatening to unplug Antarctic glacier outlets, potentially resulting in more rapid sea level rise. The retreat of nonpolar glaciers also contributes to sea level rise. Global warming has led to decades of shrinking and thinning of the Arctic sea ice, making it vulnerable to atmospheric anomalies. Projections of declines in Arctic sea ice vary. While ice-free summers are expected to be rare at 1.5 degrees Celsius degrees of warming, they are set to occur once every 3 to 10 years at a warming level of 2.0 degrees Celsius, increasing the ice albedo feedback. Higher atmospheric CO2 concentrations have led to an increase in dissolved CO2, which causes ocean acidification. Furthermore, oxygen levels decrease because oxygen is less soluble in warmer water, an effect known as ocean deoxygenation. Many regions have probably already seen increases in warm spells and heat waves, and it is virtually certain that these changes will continue over the 21st century. Since the 1950s, droughts and heat waves have appeared simultaneously with increasing frequency. Extremely wet or dry events within the monsoon period have increased in India and East Asia. Various mechanisms have been identified that might explain extreme weather in mid-latitudes from the rapidly warming Arctic, such as the jet stream becoming more erratic. The maximum rainfall and wind speed from hurricanes and typhoons are likely increasing. Long-term effects of global warming. On the timescale of centuries to millennia, the magnitude of global warming will be determined primarily by anthropogenic CO2 emissions. This is due to carbon dioxide's very long lifetime in the atmosphere. The emissions are estimated to have prolonged the current interglacial period by at least 100,000 years. Because the great mass of glaciers and ice caps depress the Earth's crust, another long-term effect of ice melt and deglaciation is the gradual rising of land masses, a process called post-glacial rebound. This could be facilitating seismic and volcanic activity in places like Iceland. Tsunamis could be generated by submarine landslides caused by warmer ocean water thawing ocean floor permafrost or releasing gas hydrates. Sea level rise will continue over many centuries. Abrupt climate change, tipping points in the climate system. Climate change could result in global, large-scale changes. Some large-scale changes could occur abruptly, that is over a short time period, and might also be irreversible. One potential source of abrupt climate change would be the rapid release of methane and carbon dioxide from permafrost, which would amplify global warming. Another example is the possibility for the Atlantic meridional overturning circulation to slow or shut down, see also shutdown of thermohaline circulation. This could trigger cooling in the North Atlantic, Europe, and North America. Biosphere. In terrestrial ecosystems, the earlier timing of spring events, as well as poleward and upward shifts in plant and animal ranges, have been linked with high confidence to recent warming. It is expected that most ecosystems will be affected by higher atmospheric CO2 levels and higher global temperatures. Global warming has contributed to the expansion of drier climatic zones, such as, probably, the expansion of deserts in the subtropics. Without substantial actions to reduce the rate of global warming, land-based ecosystems risk major shifts in their composition and structure. Overall, it is expected that climate change will result in the extinction of many species and reduced diversity of ecosystems. Rising temperatures push bees to their physiological limits, and could cause the extinction of bee populations. The ocean has heated more slowly than the land, but plants and animals in the ocean have migrated towards the colder poles as fast as or faster than species on land. Just as on land, heat waves in the ocean occur more due to climate change, with harmful effects found on a wide range of organisms such as corals, kelp, and seabirds. Ocean acidification threatens damage to coral reefs, fisheries, protected species, and other natural resources of value to society. Higher oceanic CO2 may affect the brain and central nervous system of certain fish species, which reduces their ability to hear, smell, and evade predators. Humans. The effects of climate change on human systems, mostly due to warming and shifts in precipitation, have been detected worldwide. The future social impacts of climate change will be uneven across the world. All regions are at risk of experiencing negative impacts, with low latitude, less developed areas facing the greatest risk. Global warming has likely already increased global economic inequality, and is projected to do so in the future. Regional impacts of climate change are now observable on all continents and across ocean regions. The Arctic, Africa, small islands, and Asian megadeltas are regions that are likely to be especially affected by future climate change. Many risks increase with higher magnitudes of global warming. Food and water. Crop production will probably be negatively affected in low-latitude countries, while effects at northern latitudes may be positive or negative. Global warming of around 4 degrees Celsius relative to late 20th century levels could pose a large risk to global and regional food security. The impact of climate change on crop productivity for the 4 major crops was negative for wheat and maize, and neutral for soy and rice, in the years 1960 to 2013. Up to an additional 182 million people worldwide, particularly those with lower incomes, are at risk of hunger as a consequence of warming. While increased CO2 levels help crop growth at lower temperature increases, those crops do become less nutritious. Based on local and indigenous knowledge, climate change is already affecting food security in mountain regions in South America and Asia, and in various drylands, particularly in Africa. Regions dependent on glacier water, regions that are already dry, and small islands are also at increased risk of water stress due to climate change. Health and security. Generally, Impacts on public health will be more negative than positive. Impacts include the direct effects of extreme weather, leading to injury and loss of life, and indirect effects, such as undernutrition brought on by crop failures. Temperature rise has been connected to increased numbers of suicides. Climate change has been linked to an increase in violent conflict by amplifying poverty and economic shocks, which are well-documented drivers of these conflicts. Links have been made between a wide range of violent behavior including fistfights, violent crimes, civil unrest, and wars. Climate change may also lead to new human diseases. For example, while ordinary temperatures usually kill off the yeast Candida auris before it infects humans, 3 strains have recently appeared in widely separate regions, leading researchers to postulate that warmer temperatures are driving it to adapt to higher temperatures at which it can more readily infect humans. Livelihoods, industry, and infrastructure. In small islands and megadeltas, inundation from sea level rise is expected to threaten vital infrastructure and human settlements. This could lead to homelessness in countries with low-lying areas such as Bangladesh, as well as statelessness for populations in island nations, such as the Maldives and Tuvalu. Climate change can be an important driver of migration, both within and between countries. The majority of severe impacts of climate change are expected in sub-Saharan Africa and Southeast Asia, where existing poverty is exacerbated. Current inequalities between men and women, between rich and poor, and between people of different ethnicity have been observed to worsen as a consequence of climate variability and climate change. Existing stresses include poverty, political conflicts, and ecosystem degradation. Regions may even become uninhabitable, with humidity and temperatures reaching levels too high for humans to survive. Responses. Mitigation of and adaptation to climate change are 2 complementary responses to global warming. Successful adaptation is easier if there are substantial emission reductions. Many of the countries that have contributed least to global greenhouse gas emissions are among the most vulnerable to climate change, which raises questions about justice and fairness with regard to mitigation and adaptation. Mitigation. Climate change can be mitigated through the reduction of greenhouse gas emissions or the enhancement of the capacity of carbon sinks to absorb greenhouse gases from the atmosphere. There is a large potential for future reductions in emissions by a combination of activities, including energy conservation and increased energy efficiency, the use of low-carbon energy technologies, such as renewable energy, nuclear energy, and carbon capture and storage, decarbonizing buildings and transport, and enhancing carbon sinks through, for example, reforestation and preventing deforestation. A 2015 report by Citibank concluded that transitioning to a low-carbon economy would yield a positive return on investments. Drivers of greenhouse gas emissions. Over the last 3 decades of the 20th century, gross domestic product per capita and population growth were the main drivers of increases in greenhouse gas emissions. CO2 emissions are continuing to rise due to the burning of fossil fuels and land use change. Emissions can be attributed to different regions. The attribution of emissions from land use change is subject to considerable uncertainty. Emissions scenarios, estimates of changes in future emission levels of greenhouse gases, depend upon uncertain economic, sociological, technological, and natural developments. In some scenarios, emissions continue to rise over the century, while others have reduced emissions. Fossil fuel reserves are abundant, and will not limit carbon emissions in the 21st century. Emission scenarios can be combined with modeling of the carbon cycle to predict how atmospheric concentrations of greenhouse gases might change in the future. According to these combined models, by 2100 the atmospheric concentration of CO2 could be as low as 380 or as high as 1400 parts per million, depending on the shared socio-economic pathway, SSP, the world takes in the mitigation scenario. Reducing greenhouse gases. Near and long-term trends in the global energy system are inconsistent with limiting global warming to below 1.5 or 2 degrees Celsius relative to pre-industrial levels. Current pledges made as part of the Paris Agreement would lead to about 3.0 degrees Celsius of warming at the end of the 21st century, relative to pre-industrial levels. To keep warming below 2 degrees Celsius, more stringent emission reductions in the near term would allow for less rapid reductions after 2030, and be cheaper overall. To keep warming under 1.5 degrees Celsius, a far-reaching system change on an unprecedented scale is necessary in energy, land, cities, transport, buildings, and industry. Co-benefits of climate change mitigation may help society and individuals more quickly. For example, bicycling reduces greenhouse gas emissions while reducing the effects of a sedentary lifestyle at the same time. The development and scaling up of clean technology, such as cement that produces less CO2, is critical to achieve sufficient emission reductions for the Paris Agreement goals. Many integrated models are unable to meet the 2 degrees Celsius target if pessimistic assumptions are made about the availability of mitigation technologies. It has been suggested that the most effective and comprehensive policy to reduce carbon emissions is a carbon tax or the closely related emissions trading. There are diverse opinions on how people could reduce their carbon footprint. One suggestion is that the best approach is having fewer children, living car-free, foregoing air travel, and adopting a plant-based diet. Some disagree with encouraging people to stop having children, saying that children embody a profound hope for the future, and that more emphasis should be placed on overconsumption, lifestyle choices of the world's wealthy, fossil fuel companies, and government inaction. Adaptation. Climate change adaptation is the adjustment in natural or human systems in response to actual or expected climatic stimuli or their effects, which moderates harm or exploits beneficial opportunities. Examples of adaptation are improved coastline protection, better disaster management, and the development of more resistant crops. The adaptation may be planned, either in reaction to or anticipation of global warming, or spontaneous, that is without government intervention. The public sector, private sector, and communities are all gaining experience with adaptation, and adaptation is becoming embedded within certain planning processes. While some adaptation responses call for trade-offs, others bring synergies and co-benefits. Environmental organizations and public figures have emphasized changes in the climate and the risks they entail, while promoting adaptation to changes in infrastructural needs and emissions reductions. Adaptation is especially important in developing countries since they are predicted to bear the brunt of the effects of global warming. The capacity and potential for humans to adapt, called adaptive capacity, is unevenly distributed across different regions and populations, and developing countries generally have less capacity to adapt. In June 2019, UN Special Rapporteur Philip Alston warned of a climate apartheid situation developing, where global warming could push more than 120 million more people into poverty by 2030 and will have the most severe impact in poor countries, regions, and the places poor people live and work. Climate engineering. Climate engineering, sometimes called geoengineering or climate intervention, is the deliberate modification of the climate. It has been investigated as a possible response to global warming by groups including NASA and the Royal Society. Techniques studied fall generally into the categories of solar radiation management and carbon dioxide removal, although various other schemes have been suggested. A study from 2014 investigated the most common climate engineering methods and concluded that they are either ineffective or have potentially severe side effects and cannot be stopped without causing a rapid climate change. Society and culture. Political response. UN Framework Convention. As of 2019, nearly all countries in the world are parties to the United Nations Framework Convention on Climate Change, UNFC. The objective of the convention is to prevent dangerous human interference with the climate system. As stated in the convention, this requires that greenhouse gas concentrations are stabilized in the atmosphere at a level where ecosystems can adapt naturally to climate change, food production is not threatened, and economic development can be sustained. The Framework Convention was agreed on in 1992, but global emissions have risen since then. Its yearly conferences are the stage of global negotiations. During these negotiations, the G77, a lobbying group in the United Nations representing developing countries, pushed for a mandate requiring developed countries to take the lead in reducing their emissions. This was justified on the basis that the developed countries' emissions had contributed most to the accumulation of greenhouse gases in the atmosphere. Per capita emissions were still relatively low in developing countries, and the emissions of developing countries would grow to meet their development needs. This mandate was sustained in the 2005 Kyoto Protocol to the Framework Convention. In ratifying the Kyoto Protocol, most developed countries accepted legally binding commitments to limit their emissions. These first-round commitments expired in 2012. United States President George W. Bush rejected the treaty on the basis that it exempts 80% of the world, including major population centers such as China and India, from compliance, and would cause serious harm to the U.S. economy. In 2009, several UNFC parties produced the Copenhagen Accord, which has been widely portrayed as disappointing because of its low goals, leading poor nations to reject it. Parties associated with the accord aim to limit the future increase in global mean temperature to below 2 degrees Celsius. In 2015, all UN countries negotiated the Paris Agreement, which aims to keep climate change well below 2 degrees Celsius. The agreement replaced the Kyoto Protocol. Unlike Kyoto, no binding emission targets are set in the Paris Agreement. Instead, the procedure of regularly setting ever more ambitious goals and re-evaluating these goals every 5 years has been made binding. The Paris Agreement reiterated that developing countries must be financially supported. As of September 2019, there were 197 parties to the treaty, of which 165 are signatories. In June 2017, the Trump administration announced an intention to withdraw the United States from the Paris Agreement, with immediate cessation of implementation, but is legally obligated to remain until November 2020. In 2014, the UN with Peru and France created the Global Climate Action Portal (NASCA) for writing and checking all the climate commitments. Other policy. In 2019, the British Parliament became the first national government in the world to officially declare a climate emergency. As at September 2019, 9 countries including the United Kingdom, France and Argentina have made national declarations of a climate emergency. Climate emergency declarations have been made in 983 separate jurisdictions and local governments in 18 countries governing 212 million citizens. The Montreal Protocol, which was implemented to curb emission of ozone-destroying substances, may have done more than any other measure, as of 2017, to mitigate climate change, as those substances were also powerful greenhouse gases. Scientific discussion. In the scientific literature, there is an overwhelming consensus that global surface temperatures have increased in recent decades and that the trend is caused mainly by human-induced emissions of greenhouse gases. No scientific body of national or international standing disagrees with this view. Scientific discussion takes place in journal articles that are peer-reviewed, which scientists subject to assessment every couple of years in the Intergovernmental Panel on Climate Change reports. The scientific consensus as of 2013, as stated in the IPCC Fifth Assessment Report, is that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century. National science academies have called on world leaders for policies to cut global emissions. In November 2017, a second warning to humanity signed by 15,364 scientists from 184 countries stated that the current trajectory of potentially catastrophic climate change due to rising greenhouse gases from burning fossil fuels, deforestation, and agricultural production, particularly from farming ruminants for meat consumption, is especially troubling. In 2018, the IPCC published a special report on global warming of 1.5 degrees Celsius, which warned that, if the current rate of greenhouse gas emissions is not mitigated, global warming is likely to reach 1.5 degrees Celsius, 2.7 degrees Fahrenheit, between 2030 and 2052, risking major crises. The report said that preventing such crises will require a swift transformation of the global economy that has no documented historic precedent. Public opinion and disputes. The global warming problem came to international public attention in the late 1980s. Significant regional differences exist in how concerned people are about climate change and how much they understand the issue. In 2010, just a little over half the U.S. population viewed it as a serious concern for either themselves or their families, while 73% of people in Latin America and 74% in developed Asia felt this way. Similarly, in 2015 a median of 54% of respondents considered it a very serious problem, but Americans and Chinese, whose economies are responsible for the greatest annual CO2 emissions, were among the least concerned. Worldwide in 2011, people were more likely to attribute global warming to human activities than to natural causes, except in the US where nearly half of the population attributed global warming to natural causes. Public reactions to global warming and concern about its effects have been increasing, with many perceiving it as the worst global threat. In a 2019 CBS poll, 64% of the U.S. population said that climate change is a crisis or a serious problem, with 44% saying human activity was a significant contributor. Due to confusing media coverage in the early 1990s, issues such as ozone depletion and climate change were often mixed up, affecting public understanding of these issues. Although there are a few areas of linkage, the relationship between the two is weak. Controversy. From about 1990 onward, American conservative think tanks had begun challenging the legitimacy of global warming as a social problem. They challenged the scientific evidence, argued that global warming would have benefits, warned that concern for global warming was some kind of socialist plot to undermine American capitalism, and asserted that proposed solutions would do more harm than good. Organizations such as the Libertarian Competitive Enterprise Institute, as well as conservative commentators, have challenged IPCC climate change scenarios, funded scientists who disagree with the scientific consensus, and provided their own projections of the economic cost of stricter controls. Global warming has been the subject of controversy, substantially more pronounced in the popular media than in the scientific literature, with disputes regarding the nature, causes, and consequences of global warming. The disputed issues include the causes of increased global average air temperature, especially since the mid-20th century, whether this warming trend is unprecedented or within normal climatic variations, whether humankind has contributed significantly to it, and whether the increase is completely or partially an artifact of poor measurements. Additional disputes concern estimates of climate sensitivity, predictions of additional warming, what the consequences of global warming will be, and what to do about it. In the 20th century and early 2000s, some companies, such as ExxonMobil, challenged IPCC climate change scenarios, funded scientists who disagreed with the scientific consensus, and provided their own projections of the economic cost of stricter controls. In general, since the 2010s, global oil companies do not dispute that climate change exists and is caused by the burning of fossil fuels. As of 2019, however, some are lobbying against a carbon tax and plan to increase production of oil and gas, but others are in favor of a carbon tax in exchange for immunity from lawsuits which seek climate change compensation. The climate movement. In response to perceived inaction on climate change, a climate movement is protesting in various ways, such as by fossil fuel divestment, worldwide demonstrations, and a school strike for climate. Mass civil disobedience actions by Extinction Rebellion and Ingeland have ended in police intervention and large-scale arrests. History of the science. At first, climate was simply set by clima, the angle of the midday sun defining bands of latitude which suited different peoples. Theophrastus thought agriculture caused local climate changes. Colonists expected North America weather to match latitudes, but found winters unexpectedly harsh. Dubas in 1719, followed by Montesquieu and Hume, said millennia of farming had given Europe the temperate climate needed for civilization, and cultivation could bring rapid climate improvements to America. Colonists including Thomas Jefferson began research to confirm this warming. Savants thought the Earth had incandescent origins. In 1778 Buffon proposed climatic epochs of diminishing warmth, shown by fossils of tropical animals found in subarctic zones. Marriott had noted in 1681 that glass let through the warmth of sunlight but obstructed radiant heat. In 1774 de Saussure measured heat from the sun using his heliothermometer, an insulated box capped with 3 layers of glass, separated by air spaces, pointed at the sun for an hour. The temperature inside the box was then taken. It reached 190 degrees Fahrenheit, 88 degrees Celsius, at the top of Gramont in the Grey Iron Alps, and a slightly lower temperature in the valley below, though air temperatures were warmer in the valley than on the mountaintop. Joseph Fourier researched heat transfer including invisible infrared radiation, discovered by William Herschel in 1800, and in an innovative 1824 memoir assessed what sources heat the globe, and the balancing emission of infrared radiation. He proposed, using an analogy with de Saussure's device, a simple formulation of what was later called the greenhouse effect. Transparent atmosphere lets through visible light, which warms the surface. The warm surface emits infrared radiation, but the atmosphere is relatively opaque to infrared and slows the emission of energy, warming the planet. He also calculated that Earth's cooling from a molten state had slowed over time. Adolphe Brongniart found fossils of luxuriant tropical vegetation in coal seams, suggesting widespread warmth and higher levels of carbon dioxide during the Carboniferous. Unisfut's 1856 experiments used glass cylinders filled with different gases heated by sunlight, which could not distinguish the infrared greenhouse effect. Moist air warmed more than dry air, CO2 warmed most. So she concluded higher levels of this in the past would have increased temperatures. In the 1830s Melloni combined Seebeck's thermopile with a galvanometer to measure radiant heat transmission through air. In 1839 he noticed variations which he thought might be due to changing proportions of water vapor mounts, but did not experiment on this. In detailed research starting in 1859, John Tyndall established that nitrogen and oxygen, 99% of dry air, are transparent to infrared, but water vapor and traces of complex molecules, significantly methane and carbon dioxide, absorb infrared, and when warmed emit infrared radiation. He found that this increased with concentration of these gases up to a point when the effect became saturated. His 1861 paper proposed changing concentrations of these gases could have caused all the mutations of climate which the researches of geologists reveal and explain ice age changes. Water vapor appeared to be the main factor. His subsequent thermal research focused on molecular physics and meteorology. By then, as Humboldt noted in 1850, decades of climate measurements showed stability in North America rather than the expected improvement. Popular belief that rain follows the plow was dismissed by Cleveland Abbey in 1889. Svan Arrhenius sought a mechanism causing ice ages, starting with the understanding that water vapor in air continuously varied, but carbon dioxide came from long-term geological processes. Warming from increased CO2 would increase the amount of water vapor, amplifying its effect in a feedback process. In 1896, after laborious calculations, he published the first climate model of its kind, showing that halving of CO2 could have produced the ice age drop in temperature. His source from geology, Arvid Högbohm, had estimated industrial carbon output. From this, Arrhenius calculated the temperature increase from doubling CO2. Other scientists highlighted flaws. Engstrom said that saturation of the greenhouse effect meant adding more CO2 made no difference. Experts expected climate would be self-regulating. From 1938 Guy Stewart Callender published evidence that climate was warming and CO2 levels increasing, but his calculations met the same objections. In the 1950s military research provided new data, showing less saturation of the greenhouse effect at high altitudes. Earlier calculations had treated the atmosphere as a single layer. Gilbert Plass used digital computers to model the different layers and found added CO2 would cause warming. Hans Swiss found evidence CO2 levels had been rising. Roger Revelle showed the oceans would not absorb the increase, and together they helped Charles Keeling to begin a record of continued increase, the Keeling curve. Revelle, Plass and other scientists alerted media to press for government attention. The dangers of global warming came to the fore at James Hansen's 1988 congressional testimony. Scientific research on climate change expanded, and the Intergovernmental Panel on Climate Change, set up in 1988 to provide formal advice to the world's governments, has spurred UNPRS,